Hello everyone, today I'm going to explain how NOTAR systems actually work. NOTAR systems are a specific type of helicopter anti-torque design. It's a slightly ambiguous term because it's an acronym and it basically just stands for no tail rotor. However, the name NOTAR refers to a very specific design that doesn't use a tail rotor, so not every helicopter that doesn't have a tail rotor technically counts as a NOTAR helicopter, even though the acronym would still describe it. The NOTAR system is a very specific kind of anti-torque system not using a tail rotor, which instead uses a combination of the downwash from the main rotor and either an additional fan mounted in the fuselage or exhaust from the torque turbine used to power the helicopter. And the way it works is slightly misunderstood sometimes. The common notion is that exhaust or accelerated gas is simply led to the tip of the tail beam and let out through a nozzle which can be tilted so that the airstream can be directed, thus allowing for torque control. And this nozzle essentially does the job of the tail rotor. It counters the torque from the main rotor, and by tilting it with a minor addition of pitch torque, which you can of course counter with a thrust plate, but you can control how much yaw torque you use to counter the main rotor and thus control the yaw of the helicopter. And this is partially true. Such a nozzle is used in NOTAR helicopters and it is tilted in order to control the yaw and control the anti-torque. However, it doesn't do the main chunk of the work. There's actually an additional, less visible and less notable system used here, as there are actually slots along the tail boom of the helicopter. And these slots also let out air or gas from the same source that powers the tiltable nozzle at the end. However, this streams around the tail boom and uses a combination of the Coanda effect and the Magnus effect to produce torque countering the main rotor's torque. Now, boundary layer aerodynamic effects are rather complicated, and this is a bit of a combination, as I said, between the Coanda effect and the Magnus effect. The Coanda effect is that when air streams over a surface, similar to the Bernoulli effect, it creates a form of suction and thus moves the surface towards the side on which air is streaming over it. The Magnus effect is where a spinning cylindrical surface or a cylindrical surface with air flowing around it already can create lift similar to a high angle of attack wing without stalling. It's not very efficient because it causes a lot of induced drag, but for some applications it's usable, and in this case it's very useful. The idea being that when air streams onto a cylinder, the air streaming around the side that is moving along with the air, in the case of the Magnus effect, becomes less turbulent than the air moving against the rotation of the cylinder, and thus sticks to the boundary layer of the cylinder longer, and therefore the air streaming off the cylinder will be streaming off slightly angled, and thus create thrust. Similarly, in this case, there is already a boundary layer airstream along one side, and the air coming from the main rotor's downwash follows this airstream less turbulently than the air on the other side encountering the tail boom, and therefore the downwash is diverted sideways, which creates a force turning the tail boom and the helicopter against the torque of the main rotor, or rather towards the side with the slots letting out air, which is by design turning the helicopter against the main rotor's torque, which is a lot more efficient than the tail and nozzle. So this does the main chunk of the anti-torque work. However, it has the disadvantage that it can not be adjusted during flight very well, so in order to give the pilot control over his yaw motion, Additionally, there's usually a tail and nozzle that can be tilted and lets out some of the air, directly producing nozzle-based thrust, which can, by tilting this nozzle, be adjusted very quickly during flight, allowing the helicopter to maneuver very well. The concept itself is relatively new. There have been a few older experimental helicopters, but the actual use of this concept is mostly present in today's MD helicopters. Advantages are that the whole design is a bit simpler. You don't have complex mechanical parts in the tail. You also get more safety through that because you don't have a tail rotor that might hit terrain during a complicated landing. And it is also a bit quieter because you don't have a high RPM rotor on the outside of the helicopter. You only get a smooth airflow at the tail. Disadvantages being that the performance of the helicopter is limited. Here the performance of the tail rotor essentially depends on the main rotor's thrust. It also depends on weather conditions and sink or climb rate, as well as the overall flight situation. You can't yaw very fast with this kind of helicopter, and so depending on what kind of purpose the helicopter is being used for, this can be less safe than a tail rotor. That's why they're usually used in helicopters that operate under relatively tame weather conditions. However, for most purposes it's a rather viable concept. It's quieter, it's usually safer, and it's mostly found throughout the MD series of helicopters by McDonnell Douglas. Now I hope you found this little introduction into the actual inner workings of a NOTAR system somewhat interesting. I'm always open for any aerospace related questions or general physics related questions, and as always, thanks for watching.